Okay, we have a couple special rules for these limits. First example we're going to do is limit as x goes to 0 of sine of x over x. That's going to equal 1. First example has a 5 on the bottom, so in order to make it look like the special rule, we got to take the 5 out. It's a constant, so you can just bring it out. We have a special rule for that blue box. If you look above, it's just equal to 1. So we end up with 1/5 times 1, so it's just 1/5. The same rule applies if it's upside down. The limit is still going to be 1. In this case, we just need to bring the 5 out. And again, what you see in that blue box is just going to equal 1. So we end up with 5 times 1, which is just 5. Okay, on this next rule, we're not going to be able to take the 7 out. That's going to be stuck in there. So we just need to make sure that we have a 7x on the bottom. So what we're going to do is we're going to start by taking the 5 out. The 5 is going to come out, but it needs to be on the bottom. So you'll notice we move it to the bottom. But we need a 7 on the bottom, so we're going to take one of these 7s and we're going to bring it inside here. It's just a constant, so it can come in or it can come out. Now what you see in the blue box is just going to equal 1. If you remember, the original rule said sine of x over x. But as long as it's the exact same angle, in this case 7x, then it will still cancel to 1. After canceling what's in the blue box, we're left with 7 over 5. And that's your final answer for that one. The other example on this side is almost exactly the same. Instead of having a sine, you have a tangent. So we're going to have one more step. We have to change the tangent of 7x into sine over cosine. You'll notice that I separated them into two separate limits. That's because this limit is just going to give us 1 over cosine of 0. So that's just going to be 1 over 1. And on the other limit, we can write 7 over 7 because we need to bring one of these 7's inside. Again, the blue box is just going to cancel to a 1, so you're left with 7 over 5 as your final answer. So you see we get the same answer, and that's because the only extra thing we had was a 1 over cosine. And when you plug a 0 into cosine, you get cosine of 0, which is 1, so that extra little piece just gave us a 1. So we ended up with the exact same answer. After doing these two examples, we notice this special limit that we can start using from now on. The limit as x goes to 0 of tangent of x over x is going to equal 1. So let's use this special rule for now on the next time you see this limit. For this limit, we're going to have to factor the bottom. We'll take an x out, and we can separate that into two fractions. And we'll give each fraction their own limit. And you can see that first limit that's in the blue box, that's our special one. That's just going to give us a 1. And when I plug in a 0 into the second limit, I get 1 over 0 plus 3, so that's just 1/3. Okay, on our second example over here, we have the bottom with a 1 minus cosine squared. And we're going to change that into sine squared, but you have to look at the rule. The rule over here says sine squared plus cosine squared is 1. We would have to subtract cosine squared from both sides, and you get this new identity that says sine squared is the same as 1 minus cosine squared. So that's the reason why we can make that trade right there. Then we can separate sine squared into sine times sine, and cancel one of the signs. Now we're left with our special limit. It is upside down, but remember that's acceptable. So that limit will just equal 1. Okay, here we have three very similar examples. Remember, we're trying to use our special limit, so we want it to look like sine of x over x. So our first step is to multiply the top and the bottom by 1 over x. And we're almost there. They both have an x on the bottom, but one of them has a 2x on the top. So we're going to multiply it by 2 over 2, and so that way we can bring one of these 2's inside. Same thing with the bottom one. It needs a 3 on the bottom. So we multiply by 3 over 3 so we can bring one of these 3's inside. Okay, we can use our special rule for those two limits that are in the blue box. Those are equal to 1. So that would leave us with just the two fractions, 2 divided by 3, so 2/3 is your answer. Now the example in the middle is the same thing, it's just squared. So we're basically just going to have two of those things. So again, we can bring in the 2, we can bring in the 3, and again bring in the 2 and the 3. Okay, again, those limits inside the blue boxes are special limits, so they all cancel to 1. And we're left with 2/3 times 2/3. Okay, our third example is almost the same as the first one. It's just that it has a tangent instead of a sine. So again, that's going to give you that extra piece. Remember, tangent is sine over cosine, so you end up with a 1 over cosine of 2x. That's the only extra piece. But again, remember, plugging in a 0 into cosine just gives you 0. So that piece, that extra piece, is just going to be a 1. So you would get the same answer as the first one. This is an example of a real AP test question that you might get. And because the limit as x goes to 4 is not really affecting sine inverse, we can actually bring that limit inside. So we can evaluate the limit as x goes to 4 of f of x, then later do sine inverse of that value. So the limit as x goes to 4 of f of x, you can see the limit from the left and the limit from the right are both equal to 1. So that would give us sine inverse of 1. And we can rewrite that as sine of theta is equal to 1. Now we know what angle gives you 1 for sine. It would be 90 degrees or pi halves. So the answer to this limit is that it's equal to pi halves. Okay, earlier we did an example where you ended up squaring it, and this one is now to the power of 4. So I want to show you a little bit easier way of doing it. Since we have tangent of 2x over x all raised to the 4th power, you can just bring the limit inside and leave the 4th power on the outside. Remember, tangent is the same as sine over cosine. We also talked about plugging in 0 into cosine just gives you a 1. So this other piece is just going to be 1 to the power of 4. For that first one, we're going to write 2 over 2 so we can bring one of those 2's inside. Now we have a special rule for that blue box. That limit will just equal 1. So the inside of the first one is just going to be 2 times 1. So that's just 2. So we have 2 to the 4, which is 16, times 1 to the 4, which is times 1. So your answer for this one is just 16. Okay, for this example, the first thing we're going to do is we're going to separate this into 2 fractions. So we have this one, and we have this one. Okay, I want you to notice that they each get their own limit. And now we're going to multiply the top and the bottom of this fraction by 1 over x. So you'll have an x here and an x here. Now this angle is 2x, so I'm going to need a 2 right here. This angle is 4x, so I'm going to need a 4 right here. To make that happen, I'm going to have to multiply the top and the bottom of that one by 4, multiply the top and the bottom of this one by 2. Then I can bring the 2 inside, and I can bring this 4 inside. This 2 has to go outside, and this 4 has to go outside. So you can see we brought those constants outside. For the other limit, we have this 3, and we can bring the 3 outside. But you'll notice the angle is 4x, so I need a 4 right here. So we multiply by 4 over 4, and we can bring this 4 inside, leaving a 3 over 4 on the outside. Now those purple boxes are all special limits. If we do the limit as x goes to 0, we end up getting 1 for all of those purple boxes. Now that means we're left with 2 over 4 times 1 plus 3 over 4 times 1. Final answer, 5 over 4. Okay, for this first one, we're going to factor out a 3, because they both have a 3. We're also going to factor out a sine of x, because they both have a sine of x. You'll notice on the bottom we have x squared, but we can write it as x times x. The reason we're going to do that is because we want to break it into 2 fractions. Those are the 2 fractions we want to break it into. And this 3 can actually come down in the front of that first one. Okay, now we're to the point where we can use our special rules. This first one's just going to give us a 1. The second one's just going to give us a 0. So we have 3 times 1 times 0. And that's going to give us a 0. Now remember, for this one, it can be upside down. It can be x over sine, and that would be fine. For this limit, you can switch the order. It can be cosine minus 1, or it can be 1 minus cosine. Okay, the original limit said that the limit as x goes to 0 of sine of x over x equals 1. But we also noticed that if it was a 7x and a 7x, you would still get 1. So believe it or not, as long as the angle is the same, it's still going to equal 1. And you don't even have to have the limit as x goes to 0, as long as when you plug that in, it becomes sine of 0 over 0. Now again, it still has to be the same angle. It can't be sine of 7x over 5x. So this limit right here is also equal to 1. Here we're going to look at a couple of examples for sine of 1 over x. This is kind of a weird one. First one is limit as x goes to infinity. So as you go really, really far to the right, what is it that we're approaching? Well, it's getting closer and closer to the x-axis, so the answer for that one is going to equal 0. Now that's from looking at the graph, but how can you figure that out just by looking at the function? The limit as x goes to infinity of 1 over x is 0, so this is going to become sine of 0, and that's just 0. Okay, here's kind of a weird limit. Limit as x goes to 0, sine of 1 over x. If you just plug it in, you'd get sine of 1 over 0, so it's kind of like sine of infinity. What's happening to the sine function as you go to infinity? Well, nothing's happening. It just keeps going up and down, up and down, up and down. Goes up to 1, goes down to -1, goes up to 1, down to -1. If you look at the graph, you can kind of see the same things happening. The closer you get to 0, the graph just keeps going up and down, up and down, up and down. So the same thing's happening with the graph. So this limit does not exist. I'm going to write DNE for does not exist. Okay, the next one we're going to look at is the limit as x goes to 0 of x times sine of 1 over x. We know that the limit as x goes to 0 of this one does not exist, because it just keeps going up and down, up and down. But here's the interesting thing. The biggest number this can be is 1, and the smallest number it can be is -1. So it's just a number between 1 and -1. So that's important. This number is going to be 0. So what we have is a limit that is basically 0 times a number that's between 1 and -1. If it was 0 times infinity, we would have to figure out more. We wouldn't really know what the answer is. But this is 0 times a number that's between -1 and 1, so that's just going to be 0. And you can see by looking at the graph that the limit as x goes to 0 from both sides, it does look like it's approaching a height of 0 from both sides. So for this limit, we get 0. The other one, we want to see what happens as x goes to infinity. This height right here is 1, and so it looks like it's kind of approaching 1 as x goes to infinity. So if I had to guess, I would say 1. But we can actually rewrite this. We just multiply the top and the bottom by 1 over x. The 1 over x will cancel on top with the x. And now we're left with the limit as x goes to infinity of sine of 1 over x over 1 over x. Now this looks kind of like one of our limits. In the very beginning, we had a limit as x goes to 0 of sine of x over x, and that was equal to 1. This kind of looks like that. What I want to point out is that the angle is the same, and when I plug in the infinity, it becomes sine of 0 over 0. Remember we said if it's the same angle, and you plug in the value that x is approaching, if you can get sine of 0 over 0, then that limit will equal 1. And that's what's happening here. This limit is going to equal 1.